Hi, you 12s, welcome back. This is going to be a very important video on the Trp Operon attenuation. Let's do a quick recap as always of our last video. We looked at structural genes, alright, so Trp E, D, C, B, and A, and how important they are in creating tryptophan. Alright. In the case of the repression model, we looked at the operator region and how the protein sits on there and might change shape if there is free-floating tryptophan. In this case, we're now looking at the leader region. Okay. Let's continue on. So as we know, in repression, all right, if there is free-floating tryptophan around, it will bind to the binding sites of the repressor protein, and that protein will change shape and then bind to the operator region, which will block polymerase from transcribing. Therefore, no structural genes and no tryptophan created. All right, you can see the same thing here. All right, let's look at attenuation this time. It's a little bit different, but it's a similar sort of ending of the process. Again, these are the dot points as per usual. Alrighty. So as we know, repression prevents transcription from starting, okay, by the repressor protein binding, whereas attenuation is a regulatory measure to prevent the continuation of transcription of the Trp Operon. Okay, so that is the difference. So transcription will occur to an extent, but then it will stop. All right. Whereas with repression, it literally doesn't even start. Okay. Again, to attenuate is to reduce the effect of something. Tryptophan availability. So this is important firstly. And this image is actually taken. I took a photo of something I drew on the board last year. Okay, so Trp Operon by repression uses free-floating tryptophan found in the cell cytoplasm. And attenuation uses bound tryptophan found in tRNA molecules. Okay, so whether there's bound tryptophan or not is what happens during attenuation. Amount of tryptophan may be low, but will never be nothing, so that's an important point. Tryptophan will never go to zero, just keep that in mind. That is important to understand. So you can see this here. All right, so in this case, what I've drawn, bound tryptophan is low, free-floating tryptophan is also low. Okay, if it was more up here, it'd be medium, more up here, high. All right, so let's get to attenuation. So we're going to zoom in here on the leader region. So we should be able to understand here that we have the operator region. So we're just looking at our tryptophan operon again. All right, so operator region, we've zoomed in on the leader region, so Trp L, and then as you can see, the structural genes start here. Okay, so that's Trp E, obviously Trp D would be here as well, etc., etc. C, B, and A. So there's 4 different regions that you can see clearly noted. Okay. Region 1, Region 2, Region 3, and Region 4. And that is on obviously both of the strands of the DNA, and then that's going to be also coded onto the strands of RNA, as you can see here. Sorry, the strand of RNA. All right. Once it's being transcribed by RNA polymerase. All right, as you can see, the ribosome is here, following in suit at the exact same time, but just a little bit behind. So transcription and translation occurs simultaneously in the tryptophan operon. Remember that, and prokaryotes. Alrighty. So what else is important here? So we have the operator region, we have the leader region with its 4 different regions or domains. Okay, or segments, any of that. But I'm going to probably refer to them as region 1, 2, 3, 4. You also have this attenuator region. Okay, and as you can see, it's made up of T's and A's. So thymines and adenines. And then, of course, when it becomes RNA, it's uracil. All right, and what's notable about this? Remember, T and A has a weaker hydrogen bond, so only 2 H bonds compared to the 3 H bonds you would find in cytosine and guanine together. Okay, so weaker nitrogenous base bonds. That will become important later. Okay, cool. So that's kind of the anatomy of it. Let's continue on now. So Trp L made up of 2 tryptophan codons. So what else can we see? All right. So UGG is the RNA codon for tryptophan, also known as ACC in DNA. And as you can see, there's the two white lines. Okay, that represents the two codons. So that's within region 1. This codon might stop the ribosome, okay, depending on something else. There's also this stop codon here, so UGA in the RNA or ACU in the DNA. So once it's transcribed, it becomes that UGA. You see that here. Obviously, if it's a stop codon, it will stop the ribosome. So the ribosome has two places it can go. Okay, it can either and stop here, or go all the way and stop here. All right, that's the two clauses. Yeah, this might happen, or this might happen, X or Y. And that depends on how much tryptophan is in free floating in the cell. Scratch that, I actually meant bound tryptophan on the tRNAs. All right, let's have a look again. So this is just another version of what we've been looking at. You can see the 4 different regions, 1, 2, 3, and 4, okay, as well as the attenuator. I'm looking at the RNA here. And then, of course, the structural genes. So regions 2 and 3 have complementary base pairings that, if not stopped, will be attracted and attach. Okay, so note 1 and 2 have complementary base pairings. 2 and 3, 3 and 4. Okay, so they all are attracted to one another. And depending on where the ribosome goes, that's where you'll see them actually come together. Okay, this pinches together the messenger RNA strand and it creates a hairpin loop. Okay, when it pinches together here like this one or like this one, you see that loop. All right, and you'll see that more clearly in the next image. So regions 3 and 4 will do the exact same process as 1 and 2. All right, or 2 and 3. All right, so let's look at attenuation when there's high bound tryptophan. So remembering, this tryptophan here is bound to the tRNAs. So you can see that here. Tryptophan here, tryptophan here, tryptophan that once was here, tryptophan that once was here. All right, there's a lot around the cell of this bound tryptophan. Cool. So what can we see has occurred? So the ribosome has come up the strand, the messenger RNA strand. All right, it's already been transcribed by RNA polymerase. So that's done its job so far. Okay, it's gone through up to the attenuator region and it has transcribed the strand into messenger RNA. Cool. Our ribosome has come across. All right, if I just rub this one out. Our ribosome has come across. All right. And it started the translation process and it is stopped at its first checkpoint. Its first checkpoint are the 2 tryptophan codons. Obviously, we have the tryptophan here that go into the codons because there is a high amount of bound tryptophan. All right. Which means that the ribosome will then pass its checkpoint and continue on to the stop codon. Stop codon will always stop the ribosome. Okay, so that's not going anywhere from now on. All right, let's rub all this out. So what are we looking at? We're looking at our ribosome here. Okay, it's now in the middle of somewhere. Where is it? So it's covering the middle area and part of region 1 and region 2 of the leader region. All right, so what is that doing in the end? That is now stopping the connection of region 1 and 2 that are attracted to one another. That's now blocked by this ribosome. Okay, so they can't attract to one another and they can't create a hairpin loop. So what does that mean? That means further up the strand or further towards the 3' end of the strand where RNA polymerase has added the nucleotides, that you should be able to see here that region 3 and 4 have now come together. Okay, they are attracted to one another with all those bonds, and that has occurred. All right, so tick, that has now occurred. So what does that do if there's a hairpin loop? In this scenario, it then pulls on the attenuator region, big pull. And remember, the T's and A's together, they have those weak bonds. So, in other words, A's and U's have weak bonds too. All right, so what happens? That tears the actual strand, and the RNA polymerase goes flying off. Okay, so as you can see, it's represented by it's being flung off here. Okay, all because that ribosome is sitting here blocking 1 and 2. So if RNA polymerase has flung off, kaboom, see you later. What is not occurring? The structural genes are now here, and as you can see through these little nucleotides here, the structural genes are not being transcribed and therefore will not be translated. Okay? Because the messenger RNA essentially stops here at the attenuator region. Awesome. So that's what happens if there's high bound tryptophan. All right? So no creation of structural genes occurs, so therefore energy is not expended creating tryptophan. All right, let's continue on. So this is a very similar looking image, but now we have low bound tryptophan. So what does that mean? That means there's no tryptophan on any of these tRNA molecules. There's a low amount. Okay, there may well be on one over here. Okay, but that can't reach the operon in time. Okay, so there's a low amount of bound tryptophan, not 0, but low. So what's the difference? Okay, the difference is essentially what's occurring at these 2 tryptophan codons. So there's 2 tryptophan codons here that we saw before. 1, 2. All right, but there's no tryptophan. So what occurs? So the transcription has already occurred via the RNA polymerase running down the strand, and now the ribosome is coming to do its job again. It's translating. All right, it gets to the checkpoint, but it gets stopped this time. Stopped at the checkpoint. It can no longer go any further. So if I wanted to go this way, no. Well, because there's no tryptophan to gain from anywhere. Okay, there's none here. There's none here. There's none here. So the protein stops being created. All right, the polypeptide stops being created. So what does that mean? Okay, remembering there's low bound tryptophan. So what does that mean? The ribosome stops here instead of here. Okay, it doesn't journey all the way to the stop codon. So now where is it sitting? It looks a little bit different this time. It's just sitting on region number 1 of the leader region. So therefore, as region number 2 is transcribed, and then region number 3 is transcribed, they will then have their complementary base pairs and they will connect together. Okay, so you can see that there. They connect together, and what occurs? There's a pull again that occurs here. All right, a big pull by the hairpin loop being created, but in this case, the pull is actually pulling on region 4, which is just a bunch of random jumbled nucleotides and therefore random jumbled nitrogenous bases. Okay, and it is not pulling on the weak attenuator region. Okay, if it's not pulling on the weak attenuator region, that means it's not going to break. Okay, this area will not break. This area will break. So in other words, it pulls, it doesn't break, RNA polymerase continues on its journey because it doesn't get flung off the DNA strand. All right, keeps on adding its nucleotides at the 3' end and continues to transcribe all of the structural genes, which is the really, really important part. Big tick for that. Okay, structural genes are then transcribed All right, and what do we get from that? We get charismate turning into tryptophan. Okay, and there you go. Tryptophan is finally made. It might be energy expensive, but in this case, the cell needs it. Okay, so that's the Trp Operon via attenuation when we look at high and low bound tryptophan. All right, so it gets stopped if it's high tryptophan, high bound tryptophan, and if it's low bound tryptophan, the attenuation doesn't occur, so therefore it doesn't get stopped, and transcription and translation of the structural genes occurs, therefore charismate gets turned into tryptophan. Tryptophan is now made. All right. Again, if you have any questions or comments, leave them down below. Ask me, like, comment, subscribe. Thank you for watching.